So let us start on with the foundations of natural language processing. And this is the broad agenda of what we will see in terms of basic NLP. We will understand some basic NLP. What is it? How is it different from the types of problems that we have solved so far? Because all of what we have seen until now, we have focused primarily on structured data, data in tabular format, data in rows and columns. We will understand the terms that are tokenization, vectorization. We will see that. We will look at what is the different types of pre-processing techniques. How do we pre-process and do data cleaning when it comes to text data? We'll build some intuition around that. And then we'll also get into a very, very powerful technique called word-to-vec embeddings. What are word vectors and what are embeddings? So that is the other aspect that we will talk about. So this is just to list out the general agenda, what we will be covering with respect to basic natural language processing. Now, I'm going to take an example for all of you to explain the process, how it's happening. So let's say we have a text. Let's say we have a text, Hyderabad is the capital of Telangana. This is the text that I'm giving you. Now, one very important thing that you have to keep in mind is machines cannot understand text data. Machines can only understand numbers. Even if you have categorical data, if you remember our discussion from the first day when I was covering these topics, I mentioned something very similar. I told you that time as well that machines cannot work with categories. Machines cannot work with strings. Machines can only work with numbers. Machines can only work with numeric data. If you have something which is in a categorical format, if you have something which is a string type of data, a category, let's say city name, you have to make it a point to convert that to a number. And we talked about techniques like one-hot encoding, label encoding, if you recall. The same idea applies for strings also. If you have a string, machines cannot understand strings because behind the scenes, all the different machine learning algorithms, they are all working based on some kind of mathematical equations at a very high level. And there is some kind of loss functions, there is some kind of optimization we are doing, right? So there is some kind of math that is going on behind the scenes inside NumPy arrays. There are mathematical arrays inside which math operations are happening. So naturally, you cannot work with text data. You cannot work with string data. There has to be some inherent ability to convert this into numbers. How is that happening? Let us see that. Let us learn that. So the very first thing that we do is we take the entire text. In this case, Hyderabad is the capital of Telangana. We take the whole text data and we perform a process that refers to as tokenization. What is tokenization? Tokenization is the process where you take the entire text data. So tokenization is the process where you take the entire text data and we convert the entire text data into numbers. That is what we refer to as tokenization. So tokenization is the process where we take the entire text data and we convert the text data into numbers, into unique tokens. I'm sorry, unique tokens. Numbers is the next part. So it's the process where we take the whole text data and we divide it into tokens. Tokens are effectively the smallest individual elements of a text. It could be words, it could be characters. And here you can see the example, what we have done. We've taken the text and we have divided them into tokens. Every individual word is like a token. So these are the 6 tokens that we see in the text. And there can be different ways of tokenizing, but here we are just doing the word tokenizer. Now we have to somehow figure out a way to take these tokens and give it to the ML models. And this is the machine learning model could be any of the things that we have talked about thus far. We can look at a supervised learning model like a logistic, decision tree, random forest, gradient boosting, or we can look at an unsupervised learning model like a k-means clustering. We can use any of the different approaches that we have discussed so far. So we can take that text data in a tokenized form and we have to feed it to the ML model. But remember, we have to somehow convert it to numbers. Machine learning can only work with numbers. The maths can only work with numbers. It cannot work inherently with categories or text. The first part is tokenization, where we break it into chunks, where we break it into individual words. And the second part is what we refer to as vectorization, which is the process of converting each token into a number. And how do we do that? How do we take each and every text and convert this into a numeric form? This process is what we call vectorization. And there are many, many ways of doing that. So we'll start off with a very basic approach, an approach that has been widely used in the field of natural language processing for decades. We will start with a very basic approach, a very naive approach, and from there we look at more and more advanced approaches. And then when we study neural networks, we will discuss approaches using deep learning. But in all of these approaches, this idea still remains the same. Okay, so in the field of NLP, all the approaches that we see, the core idea still remains the same, where the first step is you are tokenizing the data, you're breaking it into individual chunks, you're breaking the entire text data into individual chunks. That is what we refer to as tokenization. That is the first part. And the second part is after you do tokenization, you are trying to vectorize the data. You're trying to vectorize the data and you're trying to convert that data into individual, into numbers. Now let's understand how are we doing that? How are we actually doing the vectorization? So one of the very first things here is to build what we call a vocabulary. What is a vocabulary? Vocabulary is referred to as the unique words in the entire data set. So you have, let's say, a lot of text with you, and you go through all the sentences, you go through all the tokens across all the sentences, and you find out what are the list of unique words. Okay, so what do I mean by this? Let's take an example. Let's say we have data set one, which is he is a good boy, she is also good. So imagine we are working with a review case study, e-commerce reviews. So you buy a product in Amazon and you give a review. And second is you buy, another person buys a product in Amazon and he or she gives a review. I'm just giving an example. So let's say review one is, and document can be anything. We are looking at one more very new terminology right now called a document. What is a document? A document is simply one row or one observation. So in the field of natural language processing, one document stands for one row or one observation. That is what one document stands for. So here, one document can be one review. You write a review in the e-commerce platform, so that is one document. One document can be one review. One document can be one Facebook post. One document can be one Twitter tweet. So this is what each and every document can be, right? A document can be a review. It can be a Facebook post. It can be a Twitter tweet. A document can be an article. One document can be one article. One document can be one news story. So one document corresponds to one news story. That is how we define a document. One document is an is a so one document corresponds to uh, one article. So this is how we define a document. A document is an observation. So you go through the two documents right now and you find out what are the list of unique words across both the documents. Or in other words, what are the list of unique tokens? Because remember, I told you, as per the basic approach we are following, one token is one word. It can be different also, but here we are saying that one token is one word. So you go through all the documents in your data set and you find out that, hey, what other list of unique tokens do we have? And that is what we call a vocabulary. Okay, so you build a vocabulary. You first find out a vocabulary. And in a real world scenario, imagine you're working with real Amazon reviews data and you're going through tens of thousands and hundreds of thousands of customers who have written reviews across different products that they have purchased. And if you go through all those hundreds and thousands of reviews, and if you find out what are the list of unique words, the vocabulary will easily run into several tens of thousands of words, right? Because if you try to find out the list of unique words that people have used across their reviews, then you will find lots of unique words. So that is what we call the vocabulary. Now, what we will do is we will these are the broad approaches that we have. We have multiple approaches. Bag of words is the broad approach that we will use. There are many ways we can do this. And what is bag of words? Bag of words is a very simple feature extraction technique. This is the simplest one, where we try to understand text in the form of word counts. So we try to understand this text in the form of word counts. So we will find out the unique set of words, which is the vocabulary, and then we will find out how many times does a particular word appear in a particular document. We will simply look at the word counts. So we will represent each document by measuring the presence or absence of vocabulary words. And as you can see, this completely ignores the grammar or structure in your data. The corresponding grammar or the structure in your data is completely ignored. We will not take into account the underlying grammar or the underlying structure in our data. We will completely ignore the underlying grammar or the underlying structure in our data. So that's the way how this process is working out. That's the way how this overall process is working out behind the scenes. So the grammar or the structure will be completely ignored. How is it happening? Let's see that. So we have, once again, back to the same example. We have document one and document two, and we have the two documents right now. And first thing that we do is we find out what is the list of unique words. So we create the vocabulary. Let me remove the index part. Index is just an internal way of representing the, the mappings. This is not needed for understanding. Let me remove that for a minute. And what you do after that, first you create the vocabulary, which is the list of unique words. And after that, what we do is we go and we find out that, hey, you list out every single unique word or unique token along the columns. You list out every document along the rows, and you're simply doing word counts. You're simply looking at the word counts. You're finding out how many times each and every word or each and every token is appearing in each and every individual document. It's a simple word count based model that you created. So if you see the first row, the document one, if you see the word good has come two times because the word good has appeared two times here. See the second one, like if you see the word is has come two times because it has appeared two times here. And very interesting, the word person has appeared zero times because the person is not there in document one. So you're simply measuring each and every document. You're simply representing each and every document in terms of whether certain words are present and whether certain words are absent. It's a very basic feature engineering technique, which is completely ignoring the context of the data. Just the presence or absence of vocabulary words is considered. But the real meaning of the sentence, what do the words really mean? What does the sentence really mean? The context is completely hidden. But these kinds of models were extremely popular for a long time until we had more powerful approaches, which we'll see later. But remember, this approach completely ignores the context. It completely, ignores the meaning of the word. The context is ignored. If you look at document two, Radhika is coming one time. So the word Radhika is present once. Is come one time. And the word person has come one time. Okay, and the word good has come one time. Because the word good here is present once, rest are zero. And this is what we call a document term matrix or a DTM, where you're representing every single document in each row. Each row consists of a document, and each column consists of a unique term. So each and every row we have a document. There's a document in each and every row, right? So every row we have a document, and in the column you have each and every unique term. And this is what we call a DTN or a document term matrix. Now, there are a lot of challenges with this approach. Let us talk a little bit about what are the challenges. One of the biggest challenges is, if you see, one of the biggest challenges would be with respect to the vocabulary. So if you have 100, 1000 odd documents, and if you try to find out the list of unique tokens, if you try to find out what are the list of unique words that we have across all the documents. So across all the documents, what are the list of unique words that we have? If you try to find that out, then you will see that the vocabulary size will be very large, and also you will end up having a lot of redundant words, right? A lot of redundant words which really mean nothing. And also, let's say if I do some spelling mistake, I'm just giving an example. He is a good boy, and let's say let's say I'm using a short form. Let's say for some reason I'm using a short form and I'm using GD. Instead of good, you're saying GD. I'm just giving an example, right? So we are not using the word good. But let's say instead we are using the word GD. Okay, I'm just going to show you. Let's say we are using the word GD. Now, if I do that, if I use the word GD instead, what will happen? What will happen if I use the word GD instead? So now when we look at the vocabulary, there'll be one more unique token called GD. Now I remember this token means nothing. The GD actually means nothing. It's just an abbreviation. But just because we found another unique word, because Python found there's another unique word that we have, it will not look at the meaning, right? But it will see, hey, I think there's something unique that I see called GD. So it will still create a vocabulary token for that. And when you create the DTM, you will still end up seeing a unique word like GD in the vocabulary. And this is present one time, this is present 0 time. Look at this, because GD is present once here, but GD is not present here. This is the kind of representation you will get. But obviously, GD means nothing. These are some of the challenges that you will start to see. So as you can imagine, when you are working with real text data, there is a lot of data cleaning and data pre-processing that you will have to do. So before you even start working with your data, you will have to really put a lot of effort to clean and pre-process your data. You will have to put a lot of effort to clean your data and to pre-process your data. You will have to clean and pre-process your data. So take the original text data. So you will take the original text data and you will have to clean and pre-process your data. That's the way how you will have to work it out. So that's the way how you will have to work it out. So take the data and clean and pre-process your data. That's the idea. That's the core idea how we will work with it. Now, and what is the meaning of cleaning? What is the meaning of text cleaning here? There are a couple of ways we can do that. And all of this we are doing to improve the quality of our document term matrix. Why are we talking about text cleaning? Because we want to improve the quality of our DTM. We want to improve the quality of our DTM. We want to make sure that whatever document term matrix we are getting is of high quality. So a lot of text pre-processing we will typically do. And what are some examples of text pre-processing? Well, if I have to give you an example, imagine we are working with e-commerce review data. Hey, people write all sorts of reviews, right? You go to a restaurant, you eat something, and you love the food. Let's say you love the food, you love the restaurant, you love the ambience, and you write a review which is somewhat like, "Hey, I love the food," and you share your email ID, you share your contact number, and you say, "Okay, please contact me at John so and so at email.com, gmail.com," and you will write a long review with your contact information, other things, and all that. Now, if you think about it from a real world scenario, you have shared some personal information, right? Yes, you have talked about the restaurant, you have talked about the food, which is great. All that will be part of the document matrix, DTM, the tokens. But your personal information doesn't matter, right? Let's say at the end you say my mobile number is 97499777777, whatever. So that mobile number, that 97499777777, even that will be part of my this thing. Even this will be a term in your document matrix. That's the problem. You don't want this kind of thing to happen. You might have used some special characters like star, right? You might have used some special characters like star, star. People do that all the time. They write dot, dot, dots, right? So some dot, 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 dot they will do. Now the problem is when the DTM is getting created, all these kinds of erroneous characters, all these kinds of so-called redundant tokens will find their way into the documenter matrix. So even before you do, and even before you create your DTM, you will have to take a lot of care to remove these redundant tokens or to remove these redundant characters. That is one kind of data pre-processing we will have to do. The second thing that you will have to do is you will have to make sure that you remove the stop words. You remove the stop words. What are stop words? Stop words are effectively uh, stop words are effectively high frequency words which are present in most of the documents. They are what we refer to as stop words. So stop words are high frequency words which are present in most of the documents. So for example, we are looking at words like is and the and which really do not add any meaning to the document, right? Imagine we are trying to do sentiment analysis. I'm just trying to take a very ballpark example of sentiment analysis here. Let's say let's say we are trying to do sentiment analysis. Think about it. When we do sentiment analysis, words like ease mean nothing, right? What is ease? Ease means nothing. So in real world sentiment analysis, when we are trying to perform, words like ease and the, for, they don't mean anything, right? Because these kinds of words will be there for negative reviews also. They will be there for positive reviews also. So when we do sentiment analysis for negative reviews also, the words like is and the will be there. And for positive reviews also, the words is and the will be there. So that's the way how we will have to work it out. Okay, so when you do real world sentiment analysis, we will have the words like is present for negative reviews also. And when we do real world sentiment analysis, we will have the word is that will be present for positive reviews also. That's the way how we work it out in practice. So we will have to remove these kinds of stop words. We will have to remove these kinds of high frequency words. We can remove them. Another kind of data pre-processing that we do is we do lemmatization. What is lemmatization? Lemmatization means, let's say, oftentimes, you will have different verb forms of the word, right? Action verbs. So the base word is like, which is what we call the lemma. But there are different ways the word will often be used, right? You'll have liking, likes, liked, likely. So it all refers to the same base term. They're all referring to the same base term, right? But you are using the word in different ways. That's the idea. So they're all referring to the same base term, but you are using the word in different ways. That is what we are talking about. That is what we are talking about here. So how you do that is you can convert all of them into the same base word called like, because otherwise what will happen, you will end up getting individual columns for these words. So for liking, you will have a separate column. You'll have separate tokens, right? They'll be treated as separate tokens, but it's not needed, right? Because they're all referring to the same base word. Because remember, I told you that this model, the approach that we are following right now, we are not focused too much on the we are not focused too much on the meaning of the word. The context of the word is not really taken into account. We are only focused on the presence or absence of certain words. So we just need to take all the similar words which are part of the same lemma and convert it back to the same lemma. This is what we do as part of lemmatization. And one of the good things about this would be that we have a cleaner DTM, we have a cleaner document term matrix. And that document term matrix is nothing but a featureization technique, right? We're just taking the text, and it's a way of doing feature engineering on text data, isn't it? So at its core, that's what we are doing. At its core, all that we are doing is we are doing feature engineering. We are performing feature engineering on text data. That is what we are doing at its core, right? So we have some text data, and we are performing feature engineering on text data. So we have some text data and we are performing feature engineering on text data. That's the idea. We are performing feature engineering on text data. That's the core idea. That's the way how we are working it out. We are performing feature engineering on text data. So now the other kinds of things we can do, we also have something similarly called stemming. Stemming and lemmatization are very similar. Only thing is in lemmatization, the lemma is usually a something that is present in dictionary. It is a meaningful word. But in stemming, there are different algorithms that are used for that. This is the kind of stuff that you will find in English Oxford Dictionary kind of thing. Like, so you look at a word meaning, and oftentimes the stem words, the base words, the lemmas will be listed out, right? And there are algorithms for it, how it's done. And if you see that if these are the original words, the word stem is lick, okay, and and usually the stem is not or may not be present in the dictionary. There are different algorithms, and there are different rule-based algorithms that can be used for doing that. And this is the kind of stuff that will find its way into the dictionary. If you look up any word in the dictionary, you will typically find these word stems will also be listed out. So the idea would be to go and make sure that we take the data, we clean the data, and we all that. Okay. Uh, this is a small slide I put up here where what happens when you work with web data. Web is a very big source of text data. It's not part of the discussion here, but just wanted to mention the term that you use different Python libraries like Beautiful Soup. BS4 is a very, very popular library that you can work with. Okay, and you can scrape data from the web. Okay, so we can have data in different formats, right? I can give you some data in a CSV file. I can give you some data in a text file, whatever. But you can also scrape your data from the internet. Okay, so you can scrape your data. You have got typical HTML, right? HTML tags are there, table tags are there, body tag is there, paragraph tags are there, and you can scrape your text data. And you can pretty much do the same kind of pre-processing techniques that we are discussing. But I want to clarify one thing. I want to clarify one thing and reiterate this once again, that there are limitations to this bag of words technique. We are only taking into account the presence or absence of vocabulary words. We are just looking at the counts, how many times different types of words are present. We are only looking at the presence or absence of vocabulary words. We are just looking at the count. We are only looking at the count of how many times word one is present and how many times word two is present. We are just looking at the presence or absence of vocabulary words here. We are looking at the count of how many times this is present or how many times that is present. Just the count is what we are focusing on generally. Just the count is what we are focusing on generally. And if you see, if you look at it, if you look at these two sentences, I had washed my house and I had my house washed. Very interesting. See, these are the exact same words. You know why? Why is that the case? Because if you look at document one and if you look at document two, if you try to focus on both these documents, and if you try to follow the same approach that we listed out all this while, so find out the list of unique words. First, go through both these documents and find out what are the list of unique words. If you try to find out the list of unique words, you will observe that across these two documents, you have total 5 unique words. And if you want to create the DTM will look somewhat like this. Let me write it down for a minute. So that's your D1. I'm just going to write down the DTM for a minute. That's D1. That's D2. And these are the documents. And we have the unique words, which is I. Uh, so you will typically sort it in ascending order. So maybe you can look at the order of the words. So H, had will come before. So first you will have the word had. Then you will have the word house. Then you will have the word I. Then you will have the word my. And then you will have the word washed. See what we are getting at? See how we have managed to find out the list of unique words. Okay, and now in both these documents, each of these words are coming one time each, right? So the moment you convert these documents into a vectorized form, the moment you convert these documents into a numeric form, because that's the whole focus, right? Because we don't understand text. Machines don't understand text. We are trying to convert it to a numerical vector form. The moment you do that, the vectors look exactly the same. That's the problem because it doesn't capture the meaning, right? It's only looking at counts. So you can have two documents which have the exact same count of words, exact same number of words, but they mean completely different things. The meanings are completely different. And this is the limitation of this bag of words technique. This is the primary limitation that we will face with the bag of words technique. And obviously, despite this limitation, this approach is a very naive approach which performs really well for basic tasks. If you want to do sentiment analysis and other kinds of basic tasks like topic categorization, it performs really well. Because when you do sentiment analysis, you're looking at different terms, right? You go to a restaurant, you have some food. So oftentimes these approaches will work reasonably well. Because if a user is constantly using some negative words, then that will be highlighted. Okay. So the bag of words technique, although it is very simplistic, will surprisingly perform very well. And oftentimes it will be part of my base model. Whenever we solve real use cases, this will be usually part of my base model. So as part of the base model, we will do something like this. So now let us see how this will be applied in practice. We'll see a small example of an application How to apply this technique in practice? Let us see that in action. And there are a lot of different types of pre-processing, as I said. Like first part is you remove the stop words, you do all of that, and there's another something else called part of speech tagging. So part of speech tagging is the process where you again take the initial text data and you try to find out what are the different part of speech in that text data. That is what we refer to as part of speech tagging or pause tagging. So like we look at a particular text and we find out the different words in the text and we try to find out what part of speech they correspond to. So I look at the different words that are present in the text and we try to find out what part of speech each of the individual words correspond to. Is it a verb? Is it a noun? Is it an adverb? Is it an adjective? So each and every word that we have, what POS they correspond, what part of speech they correspond to. So every single unique word that we see, uh, we can do some pre-processing this way. And we can use a machine learning model for doing that. We don't have to manually do it. There are different ways we can do this, but we can use some pre-trained libraries for doing this part. And I'll show you a beautiful library called Spacey in a while from now. And we'll see how inside Spacey, the Spacey package, there are so many different inbuilt methods which will automatically do this for you. So you can just take the text data as it is, and you can pass it through Spacey. You can pass it through a pre-trained machine learning model that's already trained. You already have a ready-made model that is available. You can pass it through that ready-made model. Behind the scenes, it is doing classification. It is looking at each and every token or each and every word in your text, and it's trying to find out what part of speech it corresponds to. Is it a proper noun? Is it a verb? Is it a determinant? Is it a noun? Is it a proper noun? And so and so. And similarly, we can also do something called named entity recognition or NER. NER is a short form that we use. So the core idea of NER is you look at the text data and you try to find out what are the different categories of the text, what are the different categories of the words that are present in my text. That is broadly what we do as part of NER. So when we look at named entity recognition or NER, this is broadly what we do as part of NER. We go through the entire text data and we try to find out what are the different categories of the words that we have in the text. So we have, let's say, the word or the phrase Barack Obama, and that is actually a person. So again, behind the scenes, it's a pre-trained model. It's already a ready-made model that is available, that is looking at each and every collection of words, that's looking at each and every collection of phrases, and is trying to group those words into different categories. So we can say, okay, Barack Obama is a person. United States is a GPE, which is the geopolitical entity. 2009 to 17 is the date, and United States is the GPE, and this is ordinal. And there are different categories. You can Google out and see NERs. Again, there's a Spacey package which will automatically do NER for me. There are other ways of doing it. You can build your custom NER models. But behind the scenes, what we are doing is we are just doing classification. You give me some text data, and I'm trying to look at each and every word or each and every phrase in the text and trying to classify what is this, what is this, what is this. And all of these are related to feature engineering. We are simply taking that completely unstructured and dirty text data, the completely unpreprocessed text, and we are trying to find some meaning out of it. We're trying to find some meaning out of it, either by representing that in the form of word counts, by finding out how many times certain words are coming, or finding out what are the parts of speeches, or what are the named entities. So this is the core of what we are trying to achieve.